like to acknowledge the traditional custodians of the lands and waters upon which we are meeting today. We've got people from all around Australia and in fact, some people from all across the world. So we welcome you to our community. Personally, I'm down in Tasmania in the lands of the Moomere-Raymana people. And I suppose a handy resource that I like to flag to people is the IATSIS map of Indigenous Australia, which is really handy to identify the local communities that are on the lands where you may be today. So I'd like to acknowledge their elders, past, present and emerging, and their continuing contributions to our community and indeed to the power sector community as well. So today's session is about the electric vehicle project, and some of my colleagues here will talk about that in a lot more detail. We'll be running for an hour and a half today, so we're really excited to have you with us. Just to give some quick context, this project is part of a broader collaboration between Energy Networks Australia and the Australian Power Institute. It's called the Australian Strategic Technology Program, or ASTP. These are 2-year projects focused on industry-based challenges or problems that bring together university and industry-based research teams for really tightly focused 2-year projects. And so today we're lucky to have the University of Melbourne running this project, but each project can also bring in unique partners. And in this case, with the EV charging project, we have C4Net as our extra partner. So C4Net are hosting the project website where you can access some of the information about the project, including the previous webinar that we did. And for me, this is the time to actually pass to James Seymour, who is representing C4Net today, and he'll tell you a bit more about the project and about them. So thank you, and over to you, James.
Thanks very much, David, and we're delighted to be part of this project. Welcome to you all, and thank you for your interest in this seminar and the project. While the timing might be uncertain, the transition of the transport sector to 100% zero emission vehicles is well underway, and the electric vehicles will play a big part in this. This project is to benefit the entire sector, and the project sponsors are committed to keeping you abreast of not only the findings, but also the research approach taken so that we can be built upon and further developed over the years ahead. As Dave mentioned, the webinar is the second webinar since the start of the project in September last year. And the purpose of this webinar is to share the network modelling approach with the EV considerations in those models that will be used throughout the research. We appreciate that the networks have generously contributed considerable data to ensure these models are steeped in reality as much as possible. The research project runs over 2 years. It's jointly funded by Energy Networks Australia and the Centre for New Energy Technologies, or C4Net, in collaboration with the Australian Power Institute and the University of Melbourne. C4Net focuses on supporting collaborative industry-led research that helps the entire energy sector through its transition, with particular focus on utilisation of electricity data. And so EVs is a central theme for us within our portfolio. We welcome requests for support for projects, and please feel free to do so via info@c4net.com.au. We'd love you to revisit this seminar. If there's any material that is useful, be in touch with the researchers or the sponsors, and you can find the links through that website. And with that, I'll hand over to the lead researcher here, Nando, and really looking forward to this presentation.
Okay, thank you, David. Can I have the ability to share my screen? Yes, there you go. No, not yet. Not yet. I cannot share my screen yet. Host disabled participant screen sharing. Yeah, now I can. Very good. So I'm assuming that my screen is already in full presentation mode and should be possible to see. Can you confirm, please?
Yeah, all good, Nando.
All right, excellent. Well, thank you very much for joining us today. We only have 1 hour and there will be time for questions as well. So please use the chat for that. We'll go through that there. So don't wait until that moment, just start writing all your questions. So in the next 40 minutes or so, what we will try to give you is just an update on what we have been doing as part of the project, electric vehicle integration project. My name is Nando Choa, and Will as well will be presenting all these updates. So what we're going to do first is just give you a quick glimpse of what the EV integration project is about, although already was mentioned by James. Then we will start really with the aspects of electric vehicles, some basics of how they interact with distribution networks, which is infrastructure that we connect our houses to, and well, some definitions that are important, and all this concept of hosting capacity, and particularly in the context of electric vehicles. Then we will get into distribution network modeling, what we have done so far, and then some EV modeling and considerations as well, and an initial assessment of EV impacts, just for you to see what is actually that will be done in the first 6 months. Right now we're in the, well, that's not the 6 months, well, in the stage of the project where we're doing impact assessment, and we're in the first half of the impact assessment of the project, and then some key remarks. All right, so let's start with the EV integration project. So we started in September 2020. There's still a way to go. And right now we are in the part that we are calling the distribution network impacts from unmanaged EVs, meaning just normal EVs, just connecting to level 1, level 2 charging, etc., etc. And the final report for that will be in September 2021. So we're just 3 months in that block of 6 months. But part of that is a lot of modeling, and this is what we're going to present today. The project will evolve into the active management strategies of electric vehicles to increase the hosting capacity of distribution networks. And there will be a component as well of the technical economic sort of integration. So it's not just about the technicalities, but how do we look at this from the economic perspective, and not just for distribution networks, also for the whole system. The team from our side, in terms of the researchers, is led by Professor Mancarella on the technical economics, myself on the distribution network. We have Patricia and Majid as well on the customer and transport side. We have Will, Sharik supporting us, our research, as well as Carmen and Jing, and of course the support of all the distribution companies that are part of this project as well. Now let's get into the technical things. So let's discuss about electric vehicles, some definitions, increasing hosting capacity. What is this all about? So let's get to the basics first. This is just a diagram that is showing, a basic, residential LV circuit. So here in Australia is, 400 volts line to line, and then we have our single phase customers. It can be two-phase, can be three-phase as well. And well, we designed these little circuits, with what we call the after diversity maximum demand, which is the average kind of design peak value that we will assign to houses depending on the socioeconomics. And well, we just multiply by the number of houses, we produce some factors, and then that's it. That's how we actually design the transformer that we're going to have here, and then the length of that particular circuit as well, and all of that to make sure that during the peak demand, all the currents are always within the capacity of the assets, the conductors, the transformers, and the voltages as well are within, the statutory limits of that particular part of the world that we're dealing with. The thing is that when we have electric vehicles, is an excess of demand that can happen as well during the peak of those houses, and that coincident peak can create, of course, a much larger peak, and that means larger voltage drops, larger currents. Now that is not a problem per se, but if this excess demand is not within the design values that were used for this particular circuit, then we are going to have problems, of course, voltage drop problems and thermal problems. Our conductors, our transformers, our assets in general are not going to be able to handle the corresponding flows. And that's a challenge. That's the basic challenge we have with electric vehicles. And it's not just in the low voltage parts of our distribution networks. Of course, our distribution networks don't only have the low voltage, have also what we call here in Australia and in other countries, the high voltage, but it's also called internationally medium voltage. So for instance, a 22 kilovolt feeder, will have many residential and non-residential areas. And of course, the excess demand will affect the whole feeder as well. So that means that the widespread adoption of electric vehicles will create as well some challenges. And the big question, for distribution companies, here in Australia, we call them distribution network service providers, DNSPs, is to know how to determine the hosting capacity of our networks. How much electric vehicles can we have in a given network? And also, once you understand that, I mean, how can we increase that? How can we make sure that we can have as much as possible houses being able to have electric vehicles? And that's a big question. And this is what we're trying to solve in this project. Now, of course, some of you might be thinking, okay, but this is just demand. We can do what we do with other forms of demand, perhaps, and simply just disconnect when it is too much. That is true. Of course, electric vehicles will have a charging point. Today, what we call the charging point infrastructure at home will be what we call level 1 and level 2. So it depends on the number of amps that you can actually have, and this will become power depending on your voltage level, of course. But in any case, you can argue that that particular charging point could be managed because of different things, just disconnecting it based on time, disconnecting it with actual settings that come from somewhere else. Based on the charging level of the vehicle, it can interact depending on settings, or even prices can be involved. And all of that, what it means is that if we can manage that demand, well, we can reduce the overall peak, and then therefore keep our voltages and currents within the limits. That would be brilliant, isn't it? Yes, it could be done, and it's been trialed around the world in different parts. And the big question is, can we do this in a clever but also practical way? And there are many alternatives, but we need to compare those alternatives. Now, before we continue, there are some definitions that I would like to share with you. And this is not what I was planning here. This should be electric vehicle, not a PV, but anyways, it applies as well. So the electric vehicle hosting capacity, it is the maximum amount of electric vehicles that a given distribution network or part of it can host without negatively affecting its normal operation at any point in time. What is normal operation? Well, it means that our network, for that particular penetration of electric vehicles, will have the voltage statutory limits within what it is stated for that particular region of the world. Our assets are not congested, protection is okay, everything is fine. So what is normal operation will depend on all the different parameters that we consider. In our analysis, normally we will limit to our voltages and asset utilization. What amount of electric vehicles, not solar PV, this is a slide that got confused, I guess. And the idea here is that you can have a percentage of customers with electric vehicles, or the total kilowatts of charging points infrastructure being installed. And then you have solutions as well. You can have traditional and non-traditional solutions. And these are the solutions that might be implementable by distribution companies, or the solutions that distribution companies could use in the future. And this is important to discuss, because, of course, eventually what we are going to have are different types of solutions. So we're going to have augmentation, of course, or reinforcement, as is also known, or in America, they call it as wires alternative. So just more copper. And there's nothing wrong with that if it's solving the problem, but there's a cost associated to that. We can use much more cleverly our offload changers and put the taps wherever it is appropriate, according to the voltage levels. We can also use, in a better way, our zone substations or primary substations that are also known, and change for instance, the target that these OLTCs are following. We can just limit, the population to use only level 1 charging, which is not necessarily that great because level 2 is what the world is going for. But we could do this, but even using level 2 is already imposing a limit to what people can actually do in terms of charging. So distribution companies around the world are and will be doing this, because obviously this is what they know very well, and the infrastructure is ready to do it. However, there are also other alternatives, which is particularly the active control from a voltage regulation perspective of on-load changers at the primary substation or zone stations, or even using new transformers that are able to control voltages much closer to end customers, so the low voltage on-load changers, or even the active control of charging points, as I was mentioning earlier. And of course, distribution companies will be exploring this, and in some cases around the world, they are exploring this. So this is all very interesting. The problem is that we need to figure out what is the most cost-effective solution, all right? And the thing is that in reality, well, not all the solutions solve all the problems. We can, of course, definitely with augmentation, having a larger conductor, a larger transformer, we can solve all the current issues, meaning congestion problems. However, that doesn't mean that we will solve voltage problems. Same thing with managing or exploiting the offload changers. We might solve voltage problems, but not necessarily current problems. What if we play with our on-load changers in the high voltage, our primary substations or zone substations? Well, again, we are definitely managing voltages, but not necessarily the currents and the corresponding impact on the assets. What if we start really playing with different import limits, not just level 1 and level 2s? What if we start really playing with that? Well, for sure, you can calculate this very quickly, in terms of how it means in terms of your power flows and the currents, but not necessarily in terms of voltage. And you have a very sophisticated way of estimating what is the import limit, that will not affect your voltage drops. And the same thing with the non-traditional, not because we are controlling in a very active way voltages of on-load changers in the primary subs, the zone subs, or the distribution transformer. It means that we are actually doing something in terms of the thermal aspects of our conductors and our transformers. And the same thing with the active control of charging points. You can send settings in a clever way, but for you to really capture what is happening across the network, well, you need to understand what is the effects on the network. So you might be solving voltages, but not necessarily currents, or the other way around, depending on how you are doing this active control. So what I'm trying to say here or highlight is that one solution does not always address all the issues. It also depends on the network. So a rural network might have certain solutions that might be more applicable than an urban network. And also it depends on the timeline of the electric vehicle adoption. The moment that we have just a few, I don't know, a fraction of just the houses with electric vehicles, perhaps we don't need to worry that much. But if we are going to expect, electric vehicles to be adopted very, very quickly, then perhaps we need to worry about these solutions much, much quicker. But there is no silver bullet. And I'm mentioning this very confidently because we have done a similar study for photovoltaics, and it's always the same conclusion. There's no silver bullet. So we need to look at the different options and opportunities to solve the problems that come with electric vehicles. So the actual question is, what is the most cost-effective mix of solutions for a given electric vehicle penetration and type of network, which is a much more complex question, but that's reality. Things are a little bit more complex. Now, added to that is another challenge that we have when it comes to distribution networks. It is the modeling challenges. So when we look at voltages, this is a locational effect. So we need the network models, we need the impedances, the topologies. We're talking about residential electric vehicles, light-duty vehicles, vehicles that are going to be connected to a charging point installed at home, or not just at home. There are other aspects as well, but in general, in residential areas. So we need the corresponding low voltage network model. So the high voltage is not enough, the medium voltage we want to call it. We need to cater for unbalance because the effects among the phases will matter. So we need three-phase models. Demand with electric vehicles needs to be observable or understood. So we need data and models that actually capture how electric vehicles or the electricity demand of electric vehicles will look like. And if we want to start really considering different network assets that we're going to provide flexibility, like download changers, because of the voltages, well, this does add complexity. So capturing the physics of high voltage and low voltage networks is very, very important. However, in practice, unfortunately, distribution companies around the world do not have complete data and models. All right. So we don't have enough electric vehicle demand data to really say this is how they're going to look like. In all companies, at least here in Australia, it's very common to have limited quality or even availability of the low voltage circuits as well. So how can we do this sophisticated modeling and analysis if that data is not there? So these are significant challenges. And this is why the first part of the impact assessment that we're doing in this project is about the network modeling. So let's talk about network modeling now. So in this case, what I'm going to do is just to pass the ball to Will. Are you there?
Yep, Nando, thank you.
Now continue yourself. Thank you.
Yeah, hi guys. So yeah, as Nando said, I'm going to just touch on the network models we're using for this part of the project. So as Nando was highlighting, it's very important that we get both the high voltage part of the distribution network, but also the low voltage part. So in terms of the high voltage feeders we selected, there was a mixture of urban and rural from the DNSPs involved. Why? Well, we want to get a mix of the type of networks. We're never going to properly represent the vast differences in type of networks that you can get in distribution networks, but we try and do our best with what we have. So we have the data associated with those networks. So obviously we've got the topology and the electrical information and the information of the cables, the wires, that side of things. But we also importantly have the measurements, which we can use to check if our models are sensible. And we also have the number of customers on each LV feeder. So we don't have the information of the feeder itself, but we do have the information in terms of the size of the transformer, of the distribution transformer, not the primary sub. And we also have the number of customers. So that's plenty of information that we can use to create sort of pseudo LV networks based on modern design principles. So in terms of how we create these models, so every DNSP has their own way of storing their data in their own internal models. So whether that's PSS SynCal or Dig Silent Power Factory, we take that and we put that into OpenDSS, which is our sort of a modeling tool of choice for the distribution networks. And based on modern design principles and the sizes of the transformers, numbers of customers, and based on the size of conductors that you typically use in LV networks, we can build LV networks that are representative of what is likely to be there in real life. And that means we can then model down to the customer connection point, and means we have unbalanced simulations with the 3 phases, but unbalanced across the 3 phases. And then we can really get that integrated HV-LV model that we were talking about. And you can see at the bottom here, we'll go into a bit more detail on the next slide, but we've got the 4 networks. We've got 2 urban and 2 rural. So if we move to the next slide, we can have a little bit more of a think about these feeders. So firstly, we got West Hobart in Tasmania, 11 kV urban feeder. There's around 700 customers, only 12 distribution transformers and 6 kilometers of conductor. So quite a short network. The other urban feeder we've got, also 11 kV, is in New South Wales. This is around 600 customers, 17 distribution transformers, so a bit more, and a similar length in conductors as West Hobart. Then moving into the rural feeders in Hazelbrook, so New South Wales, it's 11 kV again. More customers this time, just under 1,400 customers. Now we have many more distribution transformers, so 39 distribution transformers. So that means 39 LV feeders attached to each one of those distribution transformers. And as we expect with a rural feeder, the length is a bit longer, 20 kilometers in total of conductors. And then finally Norwood, which is our rural feeder in Tasmania that we're selecting for today. And this is a 22 kV feeder, just under 600 customers, 39 distribution transformers as well, and 11 kilometers of HV conductors. So if you look on the diagrams at the top there, what this is showing you is just the HV portion of the feeder. So we've got the primary sub and then the distribution LV transformers. And if you like, on each one of those red triangles that you can faintly see would then be the LV feeder with all the customers modeled individually. Thank you. So if we move to the next slide, please. So how do we go about making sure our models are sensible? How do we translate this all into OpenDSS and that whole process of things? So first, we look at our data, right? So we select our HV feeder, whatever one we're looking at. We look at the measurements that were provided. So we've got power, reactive power, apparent power, current, voltage, all at the head of the feeder. And we look really, we want to think, okay, what's the worst case scenario for electric vehicles? Well, it's when there's a lot of demand. So we look at the peak demand day. We gather up our information for the peak demand day for our feeder. Then for each distribution transformer in the HV feeder that we saw, we assign an average peak demand for each residential customer. So in this case, from the Victorian smart meter data that was anonymized, that we have from previous projects, we know that that's around 2 kilowatts is a sort of realistic peak. So that's our sort of residential demand within the HV-LV feeder accounted for. And then we have this commercial component of load, which we don't know exactly what's going on there. You can have commercial customers of all sorts of different sizes. So then we look at the kind of the difference between the demand of where we're at with just the residential load that we do know because we know the number of customers, and then the measured demand, which we get at from the SCADA data at the head of the feeder. And then what we can do from there is we just tune the load of the commercial customers, which are spread across the different distribution transformers, until we match the data from the SCADA. Then to check everything sensible in a time series manner, we create our profile for the loads to follow. And we do this simply by normalizing the power profile that was measured at the head of the feeder. And we apply that profile to to all the customers. And then we can run power flows across the 24-hour period of our measurements. And then finally, we look at the reactive power. If there's any differences in reactive power, we can make some adjustments to our model so that matches to the model. And then we have a sensible feeder that matches up with what's being measured in reality. So if we move to the next slide, please. So this is the first example. So this is West Hobart, the urban feeder that I was talking about. And we can see that, yes, things are matching up very well. We have quite a small amount of error. Yes, the reactive power isn't perfect, but it's close. But on the impacts on currents and apparent power, it makes very little difference when we get it that close as it is. So things are looking sensible there. If we move on to the next slide, we can see, okay, that's the comparison with the measurements. How are all the assets looking? So we can see, yeah, the voltages across the whole feeder. So this is HV and LV. This is all the nodes in the feeder. That's sensible. It's what we expect. And then we can see that the utilization of the distribution transformers and the utilization of the HV conductors are sensible. They're within their limits. Now, it is quite high because this is a peak demand day, and some feeders have a much higher peak of all peaks than other feeders. So in this case, we're quite heavily loaded, but it's all making sense. So if we move through to the other feeder, so this is the rural feeder Hazelbrook. Again, similar story. The powers are matching up great. We've adjusted the reactive power to match up. We can see in the apparent power and the currents that we're very closely aligned with what is happening in reality. So that's all looking good. And if we move on to the assets on the next slide, again, we can see the voltages. Now here you'll notice the voltages are, the voltage drops are a little larger. So that large voltage drop you're seeing sort of near 1.08, that's the LV transformers. So there's a boost that most DNSPs employ on their LV transformers, bumping up to about 1.08 per unit. And then we have the voltage drop as you go down towards the end of the LV feeders for the customers. And again, if we look at the utilization of the assets, yeah, it's all looking sensible and what we expect. So if we move to the next feeder, Preston. So this is another urban feeder, similar story. We got the measurements all very close. There's a slight difference in the reactive power. We don't know if there's it's to do with an error in the measurements or a difference in load modeling, but we can see again in the current and the apparent power, which is really going to be the thing that impacts our the hosting capacity of EVs. Ultimately, if assets overload, they are very sensible and very close to what is in reality. Ultimately, we want to make sure current is within the limits and the apparent power is within the limits of the transformers and conductors within the network. So we want to make sure that's closely aligned, and it is. So our models are looking sensible for Preston. And if we have a look at the asset utilization on the next slide, again, we can see that the voltages are sensible. At the top there, we've got the LV customers, and at the bottom is the HV portion of the feeder. And again, the transformers and utilizations are sensible. Nothing's crazily overloaded. All the data seems to be lining up and making sense. So last but not least, we have Norwood. It's our rural feeder. And again, the measurements are matching the model. Reactive power is looking great. Apparent power is therefore almost identical. Current's very close. And voltage, you know, the voltage is as close as we can get it, because of course we're only modeling one HV feeder, but will actually be multiple HV feeders connected to the primary sub. And obviously there's a OLTC in action as well, which we've not modeled. So there will be a slightly difference there, but it is very close to reality in terms of what we want and what matters in terms of impacts to EVs. And finally, if we look at the assets again for Norwood, the last rural feeder in Tasmania, yeah, again, we can see that slightly higher voltage drop, which we are coming to expect in rural feeders, but it's sensible, it's what we expect. And we've got slightly higher loading in Norwood with our peak demand day from the measurements. But again, it's all sensible, it's making sense. The assets are not overloaded and business as usual, which is what we expect. So this is where I think I will hand it back over to Nando to carry on the webinar. Thank you.
Thank you very much, Will. So these feeders, these 4 feeders, well, they came from TAS network, so from TASI and from Endeavour Energy as well, from New South Wales. And this modeling was done as part of the project. We're also considering for the different assessments that we're going to carry out models that have already been created from AusNet services, that's in Victoria as well. And well, time allowing, we might also involve some feeders from Energy Queensland. But the modeling process is similar as to what has been presented today. One of the challenges clearly is the reactive power, as you might see, might have noticed, let me just go back here to some slides. So the reactive power, I mean, of course, if you look at these errors, those errors are percentage of the relative value that we are expecting at the head of a feeder from SCADA measurements. However, how this has to be looked at is its impact to the overall apparent power. And that's what matters and what was being highlighted by Will. So yes, the error relative to the actual values of the measurements are relatively high, but in the context of everything that is happening, the moment that you put the active power as well into the equation, well, it is not necessarily that significant. And it's something that we can live with. This is a challenge in general in terms of modeling. We are seeing more and more based on smart meter data as well here from Victoria, that residential customers are actually having a capacitive behavior throughout many points during the day. And this is having an effect, of course, in the overall reactive power and the corresponding behavior of the different feeders, not just at the low voltage, but also at the high voltage. So modeling is challenging, but overall, we are satisfied with the models of these particular networks. So what do we do with this is the question. Well, the next step is, of course, to consider a model for electric vehicles. And the moment you start combining everything, then, well, you run impact assessments and you start really understanding what you, well, evaluating what you could do in terms of solutions. So let's get into the electric vehicle modeling. What we are going to do in terms of the impact analysis that comes later is with data that comes from My Electric Avenue. So we're going to present that very, very briefly, but also we're going to mention what is the next step, which is data coming from another project that is more recent as well. So My Electric Avenue, for those of you that are not aware, is one of the largest electric vehicle projects that have been done in the last 10 years. And this was done in the UK from 2013 to 2015. There are some links there to some other information, reports, papers, etc. And this data covers more than 200 electric vehicles, Nissan Leaf at that time. Well, it's not, it's one of the first generations. And this data, more than 75,000 charging samples, was processed to understand, the probabilities of when people using the electric vehicles charge throughout the week, throughout the seasons, and for how long they charge, etc., etc. Everything that can actually create an understanding of how this electric vehicle demand profiles will look like. So this work was already done. I was involved in that particular research. And what we eventually can do with this particular data that is only for Nissan Leaf cars, and of course it's limited in that sense, it's only for level 1 charging, which is equivalent to 16 amps, which in the context of a 230 volt line to neutral connection is 3.7 kilowatts. And well, in this case, well, it was having a power factor of 0.98 inductive. This might change depending on the power electronics as well of the charging points. But with all this data, the moment that we can create electric vehicle profiles, it means that we can actually have those profiles for impact assessment. So we created these profiles. So we have a pool of 1,000 electric vehicle profiles based on this data, a 1 million resolution for more than 300 days. And with these profiles, what we can do is differentiate between weekdays and weekends. And what you're seeing on the left is how an electric vehicle profile will work. It's on and off because it depends on charging or discharging. And this all based on the behavior captured by the My Electric Avenue project. So you see this on and off behavior there of different colors because each depends on each car. But in the aggregate, you will have an average load, if you want, of all the different electric vehicles, in this case, 1,000. And what you're seeing here is that in the case of this level 1 charging, what you go up to in average, the moment that you have thousands of cars, in average, is around between 1 and 1.2 kilowatt. So it's around 30%, a third of the actual active power demand of a single charging point. Now, this is useful for planners, of course, but at the same time, it is not to say that for sure, the average peak demand of electric vehicles will be just that. Level 1 chargers is what it was used a few years ago. Right now, the trend around the world is to use level 2 chargers. That happens to be twice the active power demand, so twice the problem. Well, for the networks at least. All right, so this is how these profiles look like. And of course, this can be done for different seasons as well, although in this particular project, seasonality was not found to be significant, meaning throughout the seasons, the behavior was the same. Now, when you look at these profiles combined with demand, and here we're using those profiles from My Electric Avenue, yes, from the UK in this case, but it still is something reasonable to understand what might happen here in Australia. And when we combine this with actual demand from Australia, well, Victoria in this case, because we have anonymized thermometer data, what we are showing is how the demand can increase. So from let's say, a load in a peak day that goes up to around, 2 kilowatts per house, all right, in a very, very hot day. With electric vehicles, this can go up to 3. Now, it might not sound like a lot, but this is saying that everything can go actually 50% more. 50% more of load in a network that has been designed for a certain level of load can create significant problems. And this is just level 1. With level 2, expect twice the problem. Not exactly, but expect more or less like that. So that's why we need to carry out this assessment, this analysis of the corresponding electric vehicles in residential areas, urban areas, etc., etc. So that's what we're going to present in the impact assessment for 2 networks. But just before that, I just wanted to mention that we will also, we're already processing the data because of this importance of level 2 charging. This is something I was capturing another project, which is a follow-up of My Electric Avenue. It's called Electric Nation. You can go there. The data is actually publicly available, which is great, but processing it is it's a little bit painful, but we have already done it. And this data is interesting because it's not just of one type of car make. It's different makes and more than 700 electric vehicles. So it is capturing the different electric vehicle ranges or the battery sizes, and this is very interesting. But so far, our analysis suggests that there are a lot of similarities with My Electric Avenue, which is interesting. But of course, in terms of the active power demand, well, there's no similarity because it's level 2, but the behaviors are very, very similar, which is very interesting, and we will share those results as well with you in the next webinar. But let's get into the initial assessment of electric vehicle impacts. We are calling this initial assessment because this webinar was mainly to present the networks, but some of you might find that a little bit boring. So we decided to put a little bit more of meat in terms of, what does this mean, about the network model? Well, the network model is just a building block that will allow us to do the assessment of electric vehicle impacts or the assessment of the benefits from potential solutions that will diminish those electric vehicle impacts, all right? This is an initial assessment because we still are just using certain data that needs to be refined, but it will give you a sense of what is coming in the next 3 months for the assessment of all the networks that we have modeled. All right, so the methodology in a nutshell is essentially exploring different penetrations from 0 to 100. So where a penetration means like 1 electric vehicle per house. So if you have 200 houses, 100 vehicles will mean 50% of penetration, all right? So we will allocate this randomly, and then we will assess what will happen for those cases. We will also allocate residential profiles to these houses for each of the networks randomly based on the smart meter data that we have anonymized. In terms of electric vehicles, the profiles are the profiles from My Electric Avenue. We will improve them to use the Electric Nation in the near future. And then, well, we will just run power flows, given that now we have the network models, we have demand models, we have the electric vehicle demand models, so we can actually run power flows and capture with the power flows in time series all the different effects in terms of voltages and in terms of the utilization of the assets, the conductors, the transformers, etc. And then check what happens. So in terms of demand, well, I already mentioned that we're using this anonymized smart meter data. This is how it looks. More or less the average peak demand of all the profiles that we have. So that's what we were mentioning that we were using for the peak, the sunniest day, which is winter here, one of the first days, as 2 kilowatts as the average peak. However, we have the data for quite a number of days as well. And we're just selecting that peak day just to demonstrate the potential issues those particular days. Similar to when you do an analysis of solar photovoltaics, when is the maximum generation as well. So here in this case, we're expecting the largest problems to happen or the most evident problems to happen during peak days, and those happen to be during the summer. All right, so in terms of the profiles that we're using from customers, this is based on the anonymized smart meter data and looks like this in this slide. So let's get into the actual results. Here, let's start with West Hobart, that's from TASI, and that's an urban high voltage feeder where we also model, of course, the corresponding low voltages. So those numbers are just to illustrate, how big it is. The model, although it looks like, a few lines here on the right, it is a little bit more complex than that. Let's move on. So we have this model, and then when we start running the power flows, just with level 1 charging, very quickly, let me just use my pointer here. Very quickly, what you can see is that, well, in terms of electric vehicle penetration at 0, meaning nothing, well, of course, the voltages, the voltage limit being 0.94 per unit. So this is 6% below 230 volts for single phase customers. It's far from it, of course, because everything is perfectly fine. Normally, we actually boost our distribution transformers to have an extra push of voltages, and everything is fine. In terms of the utilization of the assets, is perfectly fine as well. The high voltage feeder utilization perhaps is a little bit high, but this is because it's a very, very heavy demand day. The moment that we go into 20% of electric vehicles, so 20% of the population here, or the houses with the electric vehicles, just one electric vehicle per house, what you see is that the voltages are affected, not massively necessarily. What we see in terms of the utilization of the transformers and the high voltage feeder, not much really, not significant effects. The effects start seeing or appearing much more evidently at 40 and 60% penetration, where you start seeing, well, the voltage is going slightly down, and perhaps the high voltage feeder utilization, the different conductors that we're assessing starts getting, some conductors up to 100%. So if we continue, well, yeah, voltage is still fine, transformers okay, and well, it is really the high voltage feeder, a conductor that is really carrying the aggregated, powers and the currents, of course. It gets exceeded to a little bit more than 100%, which is really negligible, to be honest, because of course our conductors and our assets in general can actually be overloaded for a few hours. So what you can conclude is that level 1 charging in West Hobart, if everyone decides to have an electric vehicle, it's not going to be a big problem, which is good news, all right? So that design of that particular urban network is EV proof, if you want, willingly or unwillingly, but it is EV proof according to this analysis. Now, right now we're picking the worst day of the year in terms of demand, which means during other days is going to be even much easier to the network. Now, if we do this in an analysis that we are going to capture what is happening throughout the penetrations, what you're seeing here about the utilization level here of the transformers, the high voltage feeder is increasing, as I was mentioning, and in terms not customer problems there. And that's good. But what happens when we move to level 2? So level 2, you already see, some significant changes here, just with 20%. And this is what is going to be a little bit worrying, because level 2 is what we're going to see predominantly across the world when people really start using electric vehicles, because no one wants to wait, 10 hours, to have the electric vehicle charge. So you would like something to be a little bit shorter. And then that's what level 2 might give you as an opportunity. So very quickly, at 20% of electric vehicle penetration, we get to values that before was only achieved with 40 and 60%. And what you can see, of course, naturally, I'm not going to go into the details, the voltages start really dropping significantly, and the load, of course, means that the utilization of our transformers and our conductors in the high voltage part is increasing and exceeding the limits. So this is really what we might see as a problem in the future. And when you do the analysis, from looking at all the customers, in terms of the evolution, of course, what we're seeing that problems are going to happen. So level 2 charging is something that will happen at very high penetrations. However, you can also argue, well, I mean, by the time that we get into 40% penetration, will take a while here in Australia, or in particular in Tassie. That's true, but it already highlights the potential challenges. Now, this is in terms of an urban feeder, where level 1 was okay, and level 2 was, well, for very high penetrations, perhaps, you can consider 40% as very high penetrations. Level 2 charging, not really that great, but still, I would call this particular urban feeder a future-ish proof, all right? Now, let's look at a rural network, all right? This is Hazelbrook. Now, when we look at this particular rural network, what we're going to see is something slightly different. Why? Because in terms of the number of customers, might be even similar in terms of the total number, but they are distributed in different ways. The feeder is longer because it's a rural feeder, and its impedances are much higher. Voltage drops are expected, to happen much quicker, or voltage rise if you have solar photovoltaics as well. But right now we're talking about loads. So the effects are different because this is a different type of network. So let's look here at first at 0% penetration of electric vehicles. So the business as usual. So already our voltages in this particular network, they are within the limits, of course, as expected, but because it's rural, already, there are voltages during the peak demand that are, let's call it relatively low, but all okay, all fine. Now, this already highlights that the moment that you have more demand, you will have problems, of course. In terms of the utilization of the high voltage conductors, they're all fine, all right? But the utilization of the transformers, because now here you have many more transformers because you have less customers per transformer, is much higher. That means, of course, the moment that you have electric vehicles, and this is level 1 charging, you start seeing, the limits increasing or being exceeded. And this is, of course, worrying. So already with a 40% of electric vehicle penetration with level 1 charging, a rural feeder, in this case, the Hazelbrook, can be compromised, particularly in terms of the transformer. Some transformer will be compromised. In terms of voltages as well, we will see problems at 40% penetration, and then that's not good. The high voltage conductor in this case, well, doesn't have problems. But let's look at level 2 charging, and then things get very worrying very quickly. So at 20% already, we have problems of voltages. And some transformers as well are compromised, meaning they are being overloaded. And of course, the moment that this goes into 40 or 60%, well, voltages are just way too low. So this is, we can run the power flow, and we're running the power flow, but this is totally unacceptable. This will not happen in reality because people will notice certain problems. The companies as well will notice certain problems with the voltages, and this will never happen. But this is just to illustrate, if we allow this to happen without any control or any limitations on the adoption of electric vehicles, or actually a solution in place. And well, of course, the problems get, to transformers that are doubling their loading, voltages that go below 0.8 per unit. So ridiculous values that will never happen in reality because we will fix things, all right? But again, it highlights the particular problems of level 2 charging, which is what we expect is going to happen in the future, and particularly in rural networks. And well, the moment that we see this distributed in the different penetrations, of course, well, the problems, as I was mentioning earlier, they come much faster, not just in terms of the transformer utilization, but also in terms of voltages. So when it comes to rural networks, this is just one, so we cannot generalize, but it gives you, a sense in this initial assessment. Well, level 1 charging, certainly, well, we are going to see problems with LV transformers and the voltages at relatively modest penetrations. Level 2 charging, problems all over the place. And well, what we hope to do is, of course, to do this similar analysis, much more thorough, of course, with the Electric Nation profiles, etc., in all these different networks that we are modeling, we'll continue to model, and well, we will share the results with you all. So just to finalize, well, some key remarks. We need adequate models, not just the high voltage part and the low voltage part, but also electric vehicle and demand to capture all these effects on customers, because that's what we want to see, how much we can have of electric vehicles without really compromising the power quality that we're giving to customers, to us, our houses. The EV impacts, clearly, I hope that you already noticed that it will depend on the type of the network. And this is why we need to assess different type of networks. Well, the next step, as I'm mentioning, is just doing this an assessment a little bit more thorough with electrification data and doing it in different feeders. So we will continue in 3 months with another webinar on all those results. So just to finalize, well, we will share these slides, of course. There are the websites of the corresponding projects from the University of Melbourne and C4Net as well. There's the report from the previous milestone that is very interesting, and the corresponding webinar as well that is available. There's this magazine article as well that might be interesting, in terms of what we did in My Electric Avenue. There's also some links to this project funded by Arena, which is about solar photovoltaics, but it will make you understand the different potential solutions that we can also apply to electric vehicles, although this is for solar photovoltaics. And then there's other links, for further reading. And with that, just let me just thank again ENA, C4Net, and API, and the University of Melbourne for their support. And of course, all the DNSPs that are involved. Thank you very much for your support and your know-how. And thank you, Jean, as well. I don't know where you're attending for your work as well with this project. And that's all for now. And then happy to answer questions. Will and I will be here, to answer your questions. Thank you very much.
Wonderful. Thank you very much, Nando. And I suppose I invite everyone now to, excuse me, share your questions. Some of you are using the Q&A function, which you can see at the bottom of your screen with the Q&A. The benefit of putting questions in there is that we can actually indicate in the recording when that question's being answered, and then people can find that later. But we do have one other question in the chat function. So it's just at a practical level, Nando, are you able to see those questions?
Yeah, I am. I can go through them. Yeah, absolutely.
Yeah. And we also have a question from Philip over in the chat as well.
Oh, there's a chat as well. Okay.
Can I just say, in terms of just the timing, Philip's question popped in a while ago. So
yeah,
on to I suppose jump on to Philip's question and then jump back to our Q&A.
Yeah, we can do that.
Encourage everyone else to pop your questions in.
All right. So yeah, any on travel patterns will differ between the UK and data. Okay, that's a very good question, Philip. Thank you. Yes, I expect there will be some differences in travel patterns. So what we wanted to do is first start capturing what has been done in very interesting projects, My Electric Avenue and Electric Nation, but we will cross-check as well with travel service here from Australia to make it more local. The problem with the travel service, which is one way of people trying to model what electric vehicles might do, because it's what normal vehicles do, is that doesn't capture the state of charge and for how long people will actually charge at home, doesn't capture many things. So perhaps having a hybrid is what would be the solution to make it more local, more to the Australian behavior. But we will look at this, and then we will be able to also answer that question, how different they are. Now moving on to the other questions. Neil made a question there as well in the chat about the level 2 charging. Yes, so the level 2 charging in this case of what I presented, Neil, was very simple. It was simply making the My Electric Avenue double the power demand. However, the data that we are going to use from Electric Nation, it differentiates the profiles from level 1 charging and level 2 charging. So that's why this is more realistic, and that's the next step. But just to show you a little bit of what is coming next, we just doubled the power demand from My Electric Avenue that was meant for level 1 only. So it was a simple assumption, but we will refine this with Electric Nation profiles that do capture how level 2 people actually behave. Moving on to Anthony on the Q&A platform there. So there are the implementation of dynamic operating envelopes. Those are solutions, Anthony. So right now we're looking at the impacts, but yes, as part of the solutions, you can argue as well, we can tell people, up to what point they can import. And yes, operating envelopes can be part of the solution. It requires an infrastructure that is very different from what we have right now, but it could be. Absolutely. I guess that the challenge there will be to what extent the charging can be modified according to that, because not all cars can actually change the internal levels of charging. Not all charging points can do that either. So there are some other questions. It's not as flexible as a PV inverter, for instance. Ben is asking, well, given increased penetration of rooftop PV at the distributed transformer, yeah, that's a very good question, Ben. So we will model as well photovoltaic installations as well in this network. So we just wanted to show you a basic, well, it's not that basic, but what we call a basic modeling of the electric vehicle impacts. But in reality, this is mixed with photovoltaics. And having photovoltaics has a challenge in any solution that you make for electric vehicles. Why? Because when you have photovoltaics and no electric vehicles, you care about voltage rise, correct? Whatever you do for voltage rise is about pushing the voltages down. But then now that you have electric vehicles, you cannot push voltages down because you're going to affect the electric vehicle, not the electric vehicle, but the voltages of homes. So you have this kind of conundrum. So we will try to address that as well in the solutions once we incorporate photovoltaics. There was also a question from Ben about market-based demand management solutions. Well, we will incorporate some pricing mechanisms, and we still need to discuss as well what other market-based solutions. But yes, this is not for the next 3 months; it's for the part after the next 3 months. So in the next 9 months, we will certainly do that. Moving to another question from Noel, are you planning to model what happens if there's strong incentive for control to recharges and start capacity? Yes. Yes, we will model the different pricing mechanisms, so incentives based on prices. So we will do that. What exactly we will do? Well, we're still right now in the modeling of the building blocks of the models, but we'll get there. It's part of the plan to consider these pricing mechanisms and incentives, etc. There's a question from Anonymous. Does your research account for Osgrid's recent trial of Jolt charging stations? Well, not really. This research, well, the presentation today is just basically the models and network models, but we are liaising with different DNSPs. You can see in the slide there, Osnet, Energy Queensland, Endeavour Energy, Gemini, Power Coast Power, United Energy, Power Link, as networks, and other DNSPs as well that are participating in this project. So we are trying to get all this information from different projects. And the thing with other projects that are happening in parallel is that the data is not going to be available necessarily in a timely manner for us. So that's part of the challenge, but we will do our best. Mohammed is asking about considering the starting current once the vehicle charges. Well, because of the power electronics, this is not like an induction motor that has an inrush current. So we just consider the charging as without any spike. It's just a normal charging, and that's a pretty good consideration based on what we have done. But I guess that's what you refer by the starting current. So hopefully I answered that question. Tim is asking what levels of embedded generation. Well, so far 0 in this example, because this is just an initial assessment. We will consider as well in coordination as well, with the different DNSPs, what would be the right level of photovoltaic generation in particular, to consider for the different penetrations for electric vehicles. So we will do that as well. There's anonymous attendee. This arena project, will there be opportunities to collaborate with that project to share data? Well, yes, that project, that's something that is different from this project, but yes, there's hopefully data to be available in the future, as well as the data from this project as well, hopefully at some point. There's finally another question from anonymous attendee: potential for capacity type storage to allow for fluctuation that maybe, well, we might not consider storage as part of the solutions because this is extra infrastructure. But definitely we will consider what particularly the electric vehicles might do in terms of providing services, and then storing that, and perhaps that's the storage that you might be asking there. So that's in part of the solutions. So right now we're in the impact assessment, so little by little, but yes, we will try to look at the potential interactions of storage that you have, of course, in the electric vehicles with potentially photovoltaics as well, and hopefully we will try to come up with some interesting things. Thank you. I think I covered all the questions very quickly, David.
Yeah, thanks, Nando. So yeah, that's the questions that we had. I encourage you again, if you've got some questions out there, please pop them in the Q&A. I suppose I'm also open it to if people have other questions for James from C4Net, or even to put him on the spot, Manaf from Energy Networks Australia there with us. If you have broader questions about the project overall or the broader innovation and research programs of the organisations. As it sits, we don't have any more questions popping through. So I suppose, I'll put a question to you, Nando. This is the second webinar that we have. What's the plan for, I suppose one question we'll get is, will the slides be available from
Yes, of course.
Yep, so for everyone, they'll be up on the C4Net project webpage. I've put the link in the chat and you should have received an email from me today with that link as well. So give us a couple of days and we'll have the video of this webinar and the slide deck up. And in terms of the next big outcome from the project, am I right, Nando, that there's a report?
That's correct.
And then there'll be another webinar. Was it as late as December or was it earlier than that?
Well, we're planning to do a webinar and a report as well. So but in addition to the report that is going to come 3 months from now, we will do the webinar as well to present all the impact assessment.
So September, September, perhaps.
That's correct. Yes.
Yeah, awesome. So yeah, if you're finding value in this project, which I'm sure you are, and thanks to Nando and Will and the team behind them, because there's lots of people involved in this, and also our industry partners as well who are helping to make this happen. If you're finding value, we hope that you keep joining us on this journey and learning from Nando and his team of experts. So I suppose our final call, any other questions for Nando or anyone else? I don't see any coming through. So I'll just reflect back. So as James from C4Net said, look, we're all very encouraging of sharing this information. If you've got any questions, we'd love you to connect and be in touch with either Nando and the team or James or myself or Manaf. So please reach out if you've got any questions. And otherwise, thank you everyone for joining us today. And thank you, Nando and Will, for your time and effort in sharing where you're up to. And thank you to ENA and C4Net for providing the support that makes all this possible. So
thank you very much, everyone.
Thanks, everyone, and see you next time, as they say.
Bye-bye.
Thanks, guys. See ya.